A very warm good evening to one and all. I am Arundhati K, second year EC student at IIIT Kottayam. It's a matter of immense pleasure and honor to see you all in this session. So let's begin our session with a silent prayer for a minute. Thank you. It's our extreme honor and privilege to have Professor Prasanta K.Panigrahi, sir, higher academic grade, Department of Physical Sciences at Indian Institute of Science Education and Research, Kolkata, as the speaker of today's session. And before we start the session, I request all the listeners to mute themselves. And in case you have any doubts, feel free to post them in the chat box. It will be looked during the Q&A session. All right. So this is our second webinar, #QThursday of our webinar series on the topic quantum technology, the technology of 21st century, which is one among the highly relevant domains with numerous applications. So let's have a look into the abstract on the same. Quantum technologies rely on purely quantum mechanical phenomena such as quantum superposition and quantum entanglement, and makes it possible to perform tasks such as teleportation and dense coding, which are impossible for the classical computers. Quantum computers employ qubits as compared to digital computers, which store data as bits or ones and zeros in binary, whereas in the former, the superposition principle opens up enormous possibilities, allowing for incredibly quick parallel and simultaneous calculations. Quantum physics states that merely looking at the system changes its characteristics. This property is widely used in developing protocols for secure communication. One of the remarkable achievements is the quantum protected encryption keys to improve communication security. For entangled systems, if one changes the attributes of one of the systems, the other correlated system changes as well. Entangled systems can be used to identify whether data transmission has been tampered with and is a resource for most of the information-theoretic tasks. Now, I would like to introduce our today's speaker, Professor Prasanta K.Panigrahi, sir, who has given excellent contributions in various fields like quantum computation and quantum information, physics of cold atoms and molecules, nonlinear dynamics, quantum field theory, wavelet transform, etc. He is ranked as one among the top 10 Indian science personalities 2017 by Scientific India for social contribution for developing an algorithm which helps in diagnosing early stage cervical cancer using artificial intelligence. He served as the associate professor and reader at Physical Research Laboratory, Ahmedabad, and also as a senior lecturer at University of Hyderabad. He also held many official positions at organizations like IISER, Kolkata, PRL, or Physical Research Laboratory, International Relations and Outreach, etc. Dr. Panigrahi has an exceptional academic experience at various institutes of national importance like NIT Patna, NIT Roorkela, Dalbagh Institute of Technology, Indian Institute of Science and Technology, IIST Trivandrum, Indian Institute of Engineering and Science Technology, IIEST Shibpur, Utkal University, Odisha, etc. He acquired his bachelor's and master's in physics from Ravenshaw College, Utkal University, Bhubaneswar. He completed his doctoral degree in field theory from University of Rochester, New York, USA, and also a postdoctoral fellowship from University of Illinois at Chicago, USA, and University of Montreal, Canada. In addition to that, he served as the editorial board member and also as a referee for various journals. Currently, he is working as a professor, higher academic grade, Department of Physical Sciences at IISER, Kolkata. So with this, we heartily invite Professor to take over the session. Sir, please. Hello, sir. Others, please mute your mic.
You are able to see my slides?
Yes, sir, it's visible.
Okay. Okay. Okay, so just give me 1 second. Just give me 1 second.
Sure, sir.
Yeah. Okay. Okay, good. So thank you very much, for your kind invitation and a kind introduction also. So I'll be talking about quantum technology in the 21st century. And all of us are familiar with quantum mechanics, starting from modern physics to regular courses in quantum mechanics. By now, quantum mechanics is by and large one old area, old subject. So why is it that now we are entering into this domain of quantum technology? Now, before we get into this quantum technology, let me just tell you that if you look at around us, most of our technology, for example, rocket, we are sending it to Moon, Mars, and even to Voyager to outside the solar system, they all depend on Newton's laws. The communication what we are doing, radio technology, television, they're all through Maxwell equations. Both of them are classical in nature, quote unquote. One is particle, because you see physical particles when they move, they satisfy Newton's laws. The other is wave phenomena. Now, in the beginning of 19th century, 20th century, there was a beautiful unification that was done between wave and particle. It was observed that at the microscopic level, you have electrons, protons, atoms, all of them behave like wave and particle. So that's the thing to keep in mind. In certain aspects, they behave like particles. In some aspect, they behave like wave. For example, they carry a finite amount of energy, quanta of energy. They behave like a particle. You can count them. 1 photon, 2 photon, 3 photon, like that. Wave, they interfere. And if you see the technology, what we are talking about, quantum technology, crucially depends on both the things. Now, as I go along, I'll tell you, for example, a little bit of history and, how the development took place. Most of the theory is well known. In fact, we are dealing with very rudimentary theory as we are developing this technology. You will see the theory that we have available at this moment do not go beyond the first or second chapter of quantum mechanics. A lot more is going to come. So if you ask, for example, in this 21st century, what are the technologies which are now available? For example, if you do a search, you can actually find out quantum key distribution, QKD machines available, quantum random number generator available. So these are manifestations of quantum technology already in the market. So now much more is going to come. So as I go along, I will start with recent progress. What has been going on right now? Just like I mentioned, 2 things there. Then I get into quantum computation and what kind of technology is coming out, introduction, timeline, the basic building block presently being used in quantum computer as called qubits. So I'll tell you a little bit about that, because I hope that some of you will be able to manipulate qubit, because machines are available by IBM and many other competitors who are building quantum computers, simulators, and many of you may be involved in these kind of things in future. So I'll introduce you to this mathematics. And I told you that in case of particles and waves, what we knew about it in classical mechanics and also in Maxwell equations, the quantum world provides unification. So superposition is a characteristic thing of particles, sorry, of the waves. You will see how it comes and gives you power in terms of parallel processing, quantum parallelism, that is parallel processing. And you have more than one particle, two particle, three particle, which can be used to build a mega quantum computer, which people are building, for example. And there, something called entanglement plays a very key role. So this I'll spend some time. What is entanglement? Completely classic quantum behavior. It is a quantum resource. You are using it for many things like teleportation. So and then I'll show you quantum computers. Many companies are now out there, IBM and this group in China. Many quantum computers are a reality. Toshiba from Japan, D-Waves from Canada. So when you talk about quantum computers, you'll find out the whole circuit looks pretty much like electronics. Okay, many of you might have taken electronics courses. You will find out that they look like electronics. So you start with a circuit kind of thing, then you apply gate, just like electronics. You have NAND, NOR, some kind of gates you apply. Fortunately, you only need two gates here, Hadamard and control lot. People have already designed those kind of things. So if you are curious, you can go to IBM, play around with these gates, design a quantum computer for yourself. People have done it. Now, when you go to quantum world, there are certain things one cannot do because you realize that there is something called unitary matrices. Whatever operation you do in a quantum world, it has to be done through unitary matrices. And certain things like you cannot do xeroxing. So no cloning in popular term is like no xeroxing. You cannot create multiple copies of the same unknown state. So certain restrictions you have to obey. So this is one of those restrictions. I'll tell you more as you go along. Okay, so some advertisement. Okay, now you people are young, and you may think that these things are for very experienced people. Answer is no. In fact, for example, this girl Yuan Tang, when she was 18, she after class 2, she went to do a summer project in Texas, and her professor showed that there is a matrix problem, which is a very fancy name called quantum recommendation problem. So some of these mathematicians, scientists from MIT, Massachusetts Institute of Technology, they have solved it. They showed the quantum computer can do it very fast. But what Yuan Tang did, and if you go through it, she was an 18-year-old kid, so she could do it, and you can very easy to understand. It's actually somewhat like a Sudoku problem. You have a two-dimensional chart where certain numbers are present, certain numbers are missing. Can you find out what are those numbers? To be more specific, since you people are, hopefully some of you will go and see her paper, you saw Yuan Tang, you can see her paper. Maybe these are the kind of things which will interest you more. You will see out what is the problem. Problem is a matrix. In matrix, two conditions are given. One condition is that low rank. If you diagonalize the matrix, you will find out only few eigenvalues are non-zero. Low rank matrix. Second, non-sparse. Most of the elements are non-zero. Non-sparse. Sparse means most of the elements are zero. So these two conditions are given. Low rank and non-sparse. What does it mean? How did we encounter matrices? We encounter matrices when we solve linear equations. Low rank really means the linear equations which are where matrix was used to solve, they are repetitions of each other. Suppose there are 4 equations, out of which only 2 are unknown. Rest 2 are repetition of the same. For example, you can have 2x plus 3y is equal to 8. 4x plus 6y is equal to 16. So it's not an independent equation. So if you have equations of this kind, you will find out the corresponding matrix will have low rank. That is, most of the equations are dependent on each other. Very good. So that big matrix which we have, most of the equations are not independent. So that information is given. Non-sparse means they are not zero. So the rest of the elements are zero. We do not know what they are. So she could solve it using a very nice algorithm due to two Indians. So I leave it for you to do a bit of a search in the net, search for you in Tang, and you'll find out that she has solved it. And you see, got a big mileage out of it. In Quantum magazine, I read it about her from the Quantum magazine, that she showed that quantum recombination problem can be solved by classical computer quite fast. So you see, the whole world is out there, and you can certainly make a contribution if you are putting your energy and come up with the right kind of problem, quantum recombination problem. Now, where is the technology? If you are following newspaper, you might have seen only a few days back, it was shown that, in India, funded by ISRO. In fact, you see it is physical research laboratory where I was part of it, and there scientists showed that you can have a free space communication. Okay, so 300 meters only right now. So between the two campuses of physical research laboratory, you found that they could communicate in a quantum channel. Okay, free space quantum communication. Why is it so nice? Because people can talk to each other, and as long as it is quantum, nobody can, get into it. You would not be able to know what is being talked about. So it can be maintained as a secret. So believe it or not, many of these diplomats and banks, president, prime minister's office already use these kind of communication channels where some enemy would not be able to know what is being talked about. You may ask, why is it so special? Why not in classical world you can do that? I'll tell you, there is some reason why quantum is unique as compared to classical world. You will see that. So now this is only very recent news that now you might have seen the budget. Budget also there is specific allocation for quantum technology. So now quantum is now there in the mainstream. You go to newspaper every other day, you hear some news about quantum. Certain technologies are already out there, and very quickly you will see satellites will be there. Countries like China, Japan, Europe, they already have quantum satellites up there, talking to each other through quantum particles like light, photons. Where India also is collaborating with Canada, and hopefully we will start with a transducer in some satellite, and eventually we will have our own satellite, hopefully. So now this is for communication, because of which ISRO is involved. And obviously defense is also involved, because communication, secret communication, banking people are involved because secret communication is very relevant for them. So now this is Professor Prasanta. You might have seen, she also had some recent thing very highlighted. Right now what I'm talking about, it will go quantum key distribution, but it is important that you can actually talk to each other through a quantum key. What is this quantum key? This quantum key is some numbers. Like, for example, you have to generate a series like 0, 0, 1, 1 kind of thing, which between you and your friend, nobody else would know. And you can code your information through this key. How do you code? You convert your information into zeros and ones, add this number, what you have called a key, and then send it. Since nobody knows about the key except you and your friend will subtract it, get the information. So security will be maintained. And you may realize that from beginning of the civilization, secure communication has played a key role. Right? Many countries have lost the war because the communication was not secure. Fascinating stories, for example, how these allies like UK and the USA broke this code of the Germans because one of the regions. And Alan Turing, you might have heard about Turing. Turing played a very key role in breaking that Enigma code. So secure communication is a very key to all civilizations since starting from the ancient times. Now, amazingly, quantum is offering a very unique way of communicating with each other in a secure manner. You will see why. And that is one of the key reasons why this research is getting so much of funding, so much of attention. Now, what is the world doing? So you go to every country, you will find out they are having their, quantum systems. For example, some small scale, big scale kind of thing. Sydney's transport network is going to be run by quantum computers. Now, Sydney has many University of Sydney. They are joining together. You have already joined together. They have joined. If some of you are interested in, going there, summer project or in some project, you will find out Sydney Hub. You can see Sydney Quantum Hub. So for quantum computer to run Sydney's transport network. Okay. Now, for example, our neighbor, Singapore, National Technological University in Singapore, they are also learning. Singapore is taking a very active interest in quantum technology. Nanyang Technological University has very strong program. SNU, Singapore National University, they have a center, quantum, you will see, which has, mini satellites and various other things. Security Center for Quantum Technology. So because Singapore, depends on modern technology for survival, because they want to survive through technology. So they are taking very active steps, something to learn from them. Okay. Now, for example, this Nanyang Technological University, they have a quantum-based chip. You see, technology now it has gone to this kind of silicon photon chips are going to replace the old computers. And very active work is going on that way. So now this one, for example, sensing technology, for example, leakage, gas leakage, those kind of sensing technology is one area. A lot of effect is going on. Okay, for example, you see this Chinese company in Shanghai Exchange. Okay, financial domain. It is also getting into financial domain. D-Wave, if you see, there's a quantum computer company called D-Waves. You can do a bit of search. They'll show you how in biological optimization program, this, that, and the financial thing, quantum computer can make a difference. Now, see, eventually, for example, you need some kind of a chip. It is still being strongly believed that silicon with photon will be the key. And for example, here there is one group. You might have, there are many other groups, which are doing it. I'm just, Australian researchers have highlighted, and they have actually taken a big lead in silicon-based quantum device. So because it will naturally replace the ones which are based on classical ones. And you see this error-free quantum computing, because error is a big problem. That because of the quantum is very sensitive, error plays a very significant role. Most of the computers are noisy, lot of error. How do you minimize the error? How do you correct the error? And if you can have a chip which is error-free, like this one here, that attracts a lot of attention. So very good. So a lot of work thing is going on. If you go to Google has its own program, Microsoft has its own program. Now, what is a quantum computer? It does computation based on principles of quantum mechanics. So you instead of, if you take a regular computer, you will find out it's basically a network. There's a register where you have 0 or 1. No voltage is 0. Some amount of voltage is 1. So, and you add those numbers. And addition more 2. For example, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 2, which is 0. That more 2 addition and this voltage in the unit of 0 and 1 is what is the basic governing mathematics and structure of any computer. Whatever you build later on, the programs, those things are up to you. Not everything is built on these numbers and addition of numbers. Unfortunately, these are creating 0 and 1 is simple. What one does is that some small amount of voltage becomes 1. Anything beyond that is cut off, so 2 becomes 0. But quantum world is very, very different. So here you have to now replace the 0 and 1 by matrices. You will see that. So the moment matrices come, for example, a column vector will come. The 0 will become 1, 0, 1 will become 0, 1. So they become vectors. How do you create them? You have to go to subatomic world. Or you have to deal with objects which are quantum, like superconducting qubits. You will see, I'll show you pictures of that. Now, why did this quantum business come into play? Because in the 90s, people saw, particularly Shor and another gentleman called Grover, I'll show you their pictures. You can do certain tasks very fast. For example, factorization. Now you will see banking technology, something called RSA, technology depended on the fact that factorization is very difficult to do in a classical computer. Multiplication is easy, but factorization is difficult. So you take a big number like 21. It's not a big one, but I'm giving an example. 7 times 3, if you multiply, you get 21 right away. But given 21 to factorize and get 3 and 7 takes more effort. And if the number is bigger, effort is more. And people have shown, mathematicians in particular, that sometimes it may take age of the universe if you have a big number to factorize into its prime factors. They are called incomplete, very difficult problems. You take exponential amount of time to solve. What was shown by Peter Shor is that, in fact, instead of exponential, you can solve it in polynomial time. If you have a quantum computer, you can actually factorize. That is a big jump from exponential to polynomial. Grover showed that when you are searching something, instead of order n, you need order root n. But nevertheless, quantum parallel processing allowed you to sort things very efficiently. These two developments in the 90s led to significant development of quantum computers. So integer factorization, discrete log problem. Okay. Now, who are the people who invested money? It was, for example, CIA in USA because of the secure communication and other kind of technology that was involved. Swiss Bank, for example, they depended on secure technology for communication. Starting from them, many other things. Now, for example, India, China. China has made huge progress. If you're curious, you go to search somebody called PAN, P-A-N. You will find out what PAN thinks today, the world thinks tomorrow. He has put multiple satellites, he has communicated with Europe, and many other things. So therefore, in a quantum computer, we have the principles of quantum mechanics. And nowadays, fortunately, instead of subatomic particles like electrons, you can actually have atoms which are like quantum dot, big kind of thing, or superconducting qubits, which you can manufacture in the lab. People have done that. That you can use and create a quantum computer. So now you need basic principles for this to operate. Superposition, as I told you, because of the wave nature of quantum particles. Same thing for interference, which happens in wave. But entanglement is a property which is basically non-separability. If you have two quantum particles, they may be created in two different states. One is separable. That means they will be separate of each other. They are not going to bother each other. Another is non-separable, namely entangled. The entangled plays a very key role. You are going to encounter it more and more. I'll show you what is it in subsequent part. Okay. So now, basically before we go, as I told you, I'll tell you some history. So as usual, it was Richard Feynman, who was always fascinated with quantum mechanics. So in 1982, he wrote a paper that if you really want to solve quantum problems, you should design a quantum computer, because quantum problems are difficult to solve. Unless a real quantum computer, you will not be able to solve. And he had difficulty in publishing that paper. Eventually, in 1982, he could publish it. It's worth reading, 1982 IJTP paper, International Journal of Theoretical Physics. And that was the idea, that he showed how to do it. Doing it needed both particle and wave nature. So that's the reason Louis de Broglie picture has put here. He found out this property quite some time ago. If you remember, Einstein in photoelectric effect pointed out that photons can behave like particles. Maxwell had shown light can show wave behavior. What de Broglie pointed out, just like light shows both particle and wave nature, every quantum particle will show the same behavior. So that was experimentally verified in 30s. So that was a major contribution. And we rely on both the aspects. Quantum parallel processing comes from wave nature, interference, those kind of things. That is what was used in 1985, who built on Feynman's idea. He did a very nice, this is quantum Turing machine. He showed that a quantum version of Turing machine is available. Turing machine is a theoretical machine based on which real classical computers were designed. The mathematical framework behind computation. What Deutsch pointed out, same thing can happen in a quantum world. It's called a quantum Turing machine. And it was a very non-trivial word. He showed you can design quantum circuits which are universal, and fortunately, he showed that these are basically matrices using which you can do it. And you need only two matrices, one 2 by 2 matrix, one 4 by 4 matrix. That was a remarkable thing, so that people really stopped getting scared about this business of quantum computers, and engineers started getting into it. You will see that led to significant development. And one of the computer scientists, person Peter Shor, if you go to his website, you will see he has given reference to a lot of nice readable papers. He showed this factorization algorithm, that instead of exponential time, quantum parallel processing can factor a big number in polynomial time. Polynomial time means you can do it. Exponential time, no, you cannot do it. So exponential to polynomial. Grover's thing was, bit more, not as dramatic as this. Instead of n steps, he showed that you can do it in order root n set. But Grover's search algorithm is very useful. You will find out, and people strongly believe that nature makes use of it. When you search, Grover gives you that this is what you are looking for in a database, and very quickly you will find out in a probabilistic way. You will zoom onto it, and very quickly with few search you will find it. So that was a major development. These two gave rise to the world of quantum computation, quantum information processing. All started this development. Feynman, David Deuce gave the foundation, but the world was not noticing. It started noticing only after these two gentlemen came and showed this. Okay. So what is this quantum computer? What Feynman was talking about? He was talking about, it was more like David Deuce, that you take your regular classical computer, replace this 0 and 1 in some numbers called column vectors. Put a ket. This bracket notation with old notation due to Dirac, Paul Edry and Maurice Dirac. We are using his notation because it's easy to use. The 0 and 1 are actually matrices. 0 is a column vector 1 0. 1 is a column vector 0 1. The moment you do it, you realize you give a name to them. They are called qubit instead of C bit, classical bit. Classical bit is 0 and 1, yes, C bit. Now, how do you find those objects? You can, any two-level system, two levels, 0 and 1. If you have access to, it will behave like a quantum system. What kind of two-level system? It could be a qubit, it could be a quantum dot, like an artificial atom, or if you can manage, take any nucleus, any atom, a nucleus. There are two levels, but electrons are difficult to manage because they move very fast, very light. So you have to instead of that, but state 0 and 1, you can take any two-level system. Just like here, these two levels, ground state, excited state. Okay. So therefore, any two-level system you could do, and if it's a quantum world, you can have a quantum computer. And if you go in reality, superconducting qubits, two different systems, so-called charge qubit and flux qubit, are being used now in present-day technology. Silicon is also maturing, silicon and light with quantum dot kind of thing. But the ones which are available, for example, IB, they're all based on this our superconducting qubit. So that's what I'm now going to point out later, superconducting qubit. I'll show you some pictures also. Okay. So I'll, for example, now machines are available. For example, this superconducting qubits. If you go, for example, if you're curious, you can check the laboratory of Professor Vijay Raghavan in TIFR. He has designed a superconducting qubit. The initial architecture came from Yale University in almost all the superconducting qubit architectures. And now, for example, IBM has adopted the same kind of architecture. Very big machines, but superconductivity is intrinsically quantum. So therefore, one can design qubits. There are only two different configurations there. One is so-called charge qubit, one is called flux qubit. Japanese people have adopted, for example, one kind of system. This IBM has another one. Now, quantum dot, I showed you the picture of this people in Australia, Sydney. Many other people are using silicon quantum dot, other kind of quantum dot for qubit. Trapped ion, 20 qubit available now in the market. In fact, Government of India, through Ministry of Information Technology, has requested many of the researchers to put up proposals, and they have allowed many of them to do quantum computation through Amazon. If you are curious, some of your teachers might have already got projects. Otherwise, we can also show you. 20 qubit trapped ion quantum computer is now available in the market. You can do your quantum computation using ion qubits. Photonic qubits are still in the lab. Defect-based qubits, topological qubits are still in the lab, but people are talking about very seriously about them. Topological qubit is more interesting because it is free of noise. The noise is a big problem. Early days, for example, that point number 7, a nuclear magnetic resonance-based qubit. This was the one which we started. You see, almost all over the world, people started with NMR quantum computation. NMR machines were available for biology and chemistry, nuclear magnetic resonance machines. In India, for example, IISc, Institute of Science, Professor Anil Kumar, he was the main person who was doing it. His students, for example, now in IISc Pune, Professor Mahesh, then IISc Mohali, and our place, Professor Ramjit Bhattacharya. They're all, products who have been trained in NMR quantum computation. So then now, making it big, some many idea things are given, including factorization, showing cloning theorem, many things. For example, 21 is equal to 7 times 3, 15 is equal to 3 times 5. Those kind of things are done there. But they cannot be extended, they cannot be made big. So once IBM came into picture, slowly people are getting out of NMR. So now, once you have qubit, let us look at, for example, same superposition in a bit more concrete way. So as I showed you, for example, vectors, you can add matrices and vectors. So the notation may look a little funny, yet, because we have to take dagger. Many of you are familiar with matrices. A column vector becomes a row vector after dagger. Dagger means transpose for complex conjugate. In quantum mechanics, psi dagger psi is normalized to 1. It physically means that the particle can be found with probability 1. It may be here, it may be there, but somewhere it is there. So the states have to be normalized. If there is a particle, psi mod psi must be equal to 1. Okay, so now, and this is linear superposition, also vector addition. If you remember, if you can add two vectors, real vectors, A and B, with some coefficients, alpha and beta, same thing here. Except this alpha beta could be complex numbers. In quantum mechanics, complex number is allowed. And this superposition is vector addition. Now this is very interesting because you see when it comes to classical vectors and this vector, mathematically there is no difference. Matrices are known. All of us have been taught matrices. They arose in the context of linear equations. So dealing with this kind of vectors is exactly the same as you deal with your own vectors. You take a dot product, A dot B. They can be orthogonal. You have unit vectors. 0 and 1 are like unit vectors. The vector A can be expanded as I times AX plus J times AY plus K times AZ. Namely, 3 components, AX and AY and AZ. I, J, K are unit vectors. Same thing here. 0 and 1 are the unit vectors in 2 dimensions. So 0, 0 is normalized 1, 1, 1 is normalized 1, just like I square is equal to 1, J square is equal to 1, K square is equal to 1, and 0, 1 is 0, just like I dot J is equal to 0. So they are mathematically identical. But what is the difference in quantum? I'll show you that. So this, although we call superposition, is nothing more than vector addition. Okay. Now, for example, this day we use a fancy word called parallel processing, quantum parallel processing. Superposition allows you 2 different ways of doing the same thing. So you can use the power of 2 qubits instead of 1 qubit, called parallel processing. Now, Grover's search algorithm and source factorization algorithm crucially depends on this. So again, so as I showed you these 2 examples, you have state 0 and 1. State 0 is here, 1 is here unoccupied. Superposition is 0 and 1. You see, it looks like a molecule. So what is the meaning of location? It is here and here. That is very unique. You will find out this kind of thing, simultaneously being here and here, is a key correlation, quantum correlation, which has puzzled many, many people, including Einstein. So this fact is a very interesting fact. Keep that in mind. EPR paradox is actually related to this. All right. So now, what is this EPR paradox? So once quantum mechanics was formulated, for example, it was realized that there are states like singlet state. You might have heard about singlet. For example, if you take H2 molecule, the 2 electrons there are in a singlet state, total angular momentum 0. So the singlet state, for example, suppose you take a particle called pi naught meson, it decays into 2 photons. Those 2 photons come out in singlet state. One, if you particle decays, for example, in a reactor in Bombay, 1 photon go to Australia, other photon could land up in USA. But strangely, both of them will be still in the singlet state. Now, this correlation is something which nobody understood. Even now also it puzzles many people. So it is called EPR, Einstein-Podolsky-Rosen paradox. This kind of non-local correlation, EPR correlation, is the one which is the heart of quantum mechanics. So this paper, 35 paper, if some are curious, please take a look at it. That this singlet state, as simple as that, their original state was not singlet. The singlet analogy was brought in by Bohm-Aharonov effect, and then later on by Bell, who formulated this, EPR paradox, quantified it using Bell's inequality. You will see that. So this, what is the big deal about the singlet state? In the singlet state, you will see there is quantum entanglement. That brings in something called quantum non-locality. I'll show you more explicitly. In some sense, even if the particles are far away from each other, they are not completely separated. One measurement and finding the particle at one place will affect the other. So I am bringing you this word called measurement. You will see that is something which is very different than the classical world. In quantum world, measurement affects the state. In classical world, suppose if you measure something is 1 kilogram, the state is not going to change. But here, if you measure, the state is going to change. Measurement crucially affects the state which you are measuring. That is uniquely quantum, because of which a lot of things can happen. And that we are going to make use of it. Sometimes it could be nuisance, because the moment you measure, things are going to change. But in fact, that if you are open-minded, the same thing can be used very effectively for doing some work for you, and you will see how. Okay, very good. Now, okay, superposition state, the moment you have, these quantum correlations will manifest. And the quantum correlation manifests in a system where there is entanglement. This entanglement is a key property of the quantum world. And that is not there in the classical domain. So that is something which you keep in mind. So what is this entanglement? Let us see. First of all, experimentally, how do you create it? As I told you, in Bombay, you have a source like a pi naught meson. Okay, and decays in 2 particles. This one, this. These 2 particle state, because of conservation of angular momentum and other kind of things, can be in certain state. For example, here, the state is given in this form. If this flow is x, the other flow is x. If this flow is y, the other flow is y. What is x and y? Their polarization. For example, if you take light or electron, spin. So spin up, spin up, spin down, spin down. And there is plus sign. If it's a minus sign, that is also possible. So the sign is very crucial. Relative sign is physically measurable. So this kind of state was created. Now this fellow is moving away. Maybe in Australia you will discover it. Maybe you will discover this fellow in Washington. So that's what I'm saying. I'm putting 2 detectors A and B to detect them, one here and one there, far, far away. What you will find, if you measure this fellow at this point, you find +1. Here also you find +1, because x and x. If it is -1, which is y, here also you find -1. So coincidence measurement, if you do, namely after you measure, if you compare, measure and compare. So this is the whole apparatus. In fact, people do it, experimentally. You measure and then compare, coincidence detector. If you do that, you will find out what you will find. Then the far away. That is the soul of EPR paradox. That Einstein didn't like it. And why this kind of correlation exists? He thought it is spooky action at a distance, which is unphysical. But it has been bugging people even now also. And but people showed one thing, that information you cannot transmit using this. Is it possible that instantaneously information can go through? Why instantaneous? Because the moment you measure one, immediately the fellow will collapse to +1. That is something, let me tell you about quantum measurement. You see, this is superposition state. After you measure, for example, you measure this object, which is Alice, Bob, Alice and Bob. You are not talking about Bob. Bob is somewhere in Washington. Alice is in Australia. You are measuring the state of Alice. You will find out the value is X or Y. But the moment you find the value of Alice is X, the state will collapse to XX because the value is not Y. Similarly, if the value is found to be Y for Alice, the state will collapse to YY. So after measurement, the superposition state will become one term, XX or YY. You see, this state is an entangled state. You cannot factorize it. But the moment you measure it, is separable. XX means X, X means they are separable. You can write X ket and X ket. They are separable. These two photons are completely separable. Whatever you do to one, the other will not be affected. Whereas if you entangle in this form, XX plus YY, there is a plus sign here. If you measure, if this flow is X, this will be X. If this flow is Y, this flow will be Y. This correlation, which is at a distance from each other, called non-local, is not exactly a local like in Bombay. One could be in Australia, one could be in Washington. This non-local correlation is the heart of quantum mechanics. Okay. Now Einstein observed it, this kind of problem in quantum mechanics, got bugged with it. Bohm actually pointed out that this can be tested, and he showed that if you take singlet, triplet kind of thing, this idea can be tested. And then came, our great man Bell, who used it to come up with inequality, measurable quantities, which was later on measured to show that quantum mechanics is always correct. So far, nobody has found mistake in quantum mechanics. But one point, collapse of the wave function takes place, no doubt. Information cannot go faster than light. So this has become a principle now that called, everything has a bound. Below, information can travel at the speed of light. There's a bound on information travel. It is not instantaneous. That you keep in mind because the collapse is instantaneous, but information cannot go immediate. Information has to go at best with the speed of light. Very good. So what are the company? Now people once, this 80s and 90s, people started playing around and designing, quantum computers using this CPR paradox. You see, people did teleportation. For example, Bennett showed in 1992, teleportation, then information space, sending of information called dense coding. It was largely due to IBM and other collaborators. Bennett, Prasad, 80s, for example, quantum key distribution, they showed without understanding deep principles of quantum mechanics. They only used this idea that measurement leads to collapse of the state. Then there are states called entangled states, which are non-separable. What can we use? And find technology. Technology was immediately started by engineers, Bennett and Prasad in particular. 80s, they showed quantum key distribution, which is now called BB84 algorithm, which is being used extensively now. Then teleportation in 1992, which have been shown experimentally. You can teleport now things to hundreds of kilometers. From Star Wars movies, you must have heard about teleportation. So something can be sent from here to there, at the speed of light, not more faster than speed of light. Now you see, many computers are available. D-Wave has been there for quite some time. Very powerful machines it has in Canada. IBM has several of them. Now they are offering to sell also. Rigetti has a simulator. Many. Google, for example, sold its chip. Toshiba, as I told you, we have access to Toshiba. It has an Ising machine, very powerful. Microsoft, you are planning to use, this topological Majorana for quantum computation. They had a bit of setback, but they are at the game. Many companies, Honeywell, Intel, and Chinese, for example, have made huge significant gain in harnessing quantum technology. It all started when the engineers came into the game. So I'll tell you a bit of story before I get into this quantum computer. So it was, for example, the classical computer, people started making smaller and smaller in size. So they came across a law, again from observation, called Moore's law, that every 18 months, you can, in the same size chip, you can put double the information. So essentially, chip size became smaller and smaller, because of which computer size became smaller and smaller. But they soon encountered, in 70s particular, that there is a lot of heating. So why heating is going on? This person, Landauer, an amazing person, he realized heating is happening because of information loss. And in fact, quantified half kT per unit of information loss. So information loss is actually behind heating. You see statistical mechanics and information theory getting correlated. And then people actually did not know exactly why this thing happened. there was this guy, Toffoli, who came up with a gate called Toffoli gate, 3 qubit. He showed that there is no heating. Now, at that time, people didn't understand why there is no heating. But there was indeed no heating. Then people found out, once they looked at it more carefully, that it is because the Toffoli gate depends on a unitary matrix. Unitary matrix are, reversible. You can take dagger and come back again. Because they are reversible, there is no loss of heat. So practically, engineers have come up with quantum circuits, quantum operators, or quantum gates which are reversible, no heating. So it's always good to move ahead, right, and do something and then see why is it for. So after those 70s development. So for example, quantum mechanics is fairly old. By 1932, it was pointed out that matrix mechanics of Heisenberg, wave mechanics of Schrödinger are identical. Dirac wrote this book, Principles of Quantum Mechanics, in 1932. All the principles, whatever you have, and nothing more we are doing. In fact, we have not gone beyond the past couple of chapters because all the technology depends only on measurement and some states, special states. But what is new? That was 1935, Einstein, EPR paradox. That paradox led to significant understanding of quantum mechanics. Bohm then had an aspect in 60s. I'll show you aspects. He showed how do you test quantum mechanics. You can in fact quantify. So people have been still doing testing of quantum mechanics because if there is a flaw, that will be very nice. For example, testing of quantum mechanics, Bell inequality, is a very active area of research. It has also generated technology because finer and finer experiments do, better and better technology can generate. So very good. So then 60s, basically theory of quantum correlation, largely because of Bell. 70s, Landauer, heat, unitary transformation as the rescue. 80s, Richard Feynman, David Deutsch, how to design a quantum computer. 90s, these two gentlemen, Shor and Grover, then it took off. And in between that, engineers came into play. Bennett and Russell, BB84, then teleportation. You see now, we are doing, only those kind of things now. So, experiments started coming in late 90s, teleportation was done, many things started from there. People are not believing that quantum computer will be possible. But you see, it is now IBM will show that indeed it is possible. So now, this quantum processing unit with the brain of a quantum computer looks like this. It's like the earlier classical computer, very big. Okay, you see here, right here. So what is it? It says chip, superconducting chip. Now, looks quite nice. This part is electronics. How the chip gets connected to the outside world, how you pull it, how it takes in signals, how it processes, all those things are done by electronics here. Very good. You can stop me at any moment if you have some questions. I will be happy to take it. Now, then, there are somewhere heat exchange takes place. So essentially, they are cooled by helium, liquid helium. So that, very low temperature. Otherwise, what will happen is that all the quantum properties will be lost. Something called decoherence. You have to cool it. Now the electronics, the broad thing is electronics, you see here. So these gold plates separate the cooling zones. And it has to be cooled to really low temperature, 1/100th of a Kelvin. So cold. That is why it is costing a lot of money. Now they talk to each other through this kind of photon carrying cables. Photon, you see, remember, the chips, they talk to each other through light. Okay. And outside world is such that it has to be protected. Protected against what? It's called decoherence. Decoherence. That plays a very significant role in spoiling the quantum computer. Now, as I pointed to you, what is the operation that goes inside? Well, basically, circuit pretty much looks like a classical computer circuit. There are, instead of 0 and 1, you will find matrix 0, 1, 0, and 0, 1. They are quantum object. So you will they will be talked to by matrices. On a single qubit, you apply some matrix called Hadamard. I'll show you exactly what it is. On 2 qubits, you apply something called control knot. These are the only 2 gates which are required to generate anything you want. That was the contribution of David Deutsch, that you need only two matrices to come up with universal quantum computation. And you will note everything in quantum world takes place through unitary matrices. So therefore, quantum logic gets reversible. You can go back, no loss of it. So unitary matrices play a significant role. Whatever you have done, it has to be done through unitary matrices. If it's not, then it's not quantum. So classical logic gates, some of them are not unique. Unitary matrices. As I told you, it was topology. If you are curious, just see 3 by 3 matrices, they are actually unitary. And he did it without understanding, but it didn't create any hit. That's how he found out that it is actually a reversible matrix. And as we came to know that it is actually a quantum object, namely unitary matrix. So now, so this reversibility and hit, keep that in mind, because people are now going to design quantum thermodynamics, quantum engines. There, these kind of things play a key role. Half KT for each information loss is the thing. Now, measurement also is irreversible. For example, if you have a superposition state, after measurement, as we saw, it becomes only one state, either XX or YY. That is also irreversible. You cannot go back. Okay, and this amazing thing that it will, after measurement, it will become only one state. XX plus YY is superposition. The moment you measure, it becomes XX or YY. That is also irreversible. But you see, measurement has changed the state. Originally, it was XX plus YY. Now it is either XX or YY. So this is very crucial. Measurement, a quantum measurement, changes the state. That is how, for example, this was first realized by Bennett and Brassard, who pointed out this fact can be useful to generate so-called key for quantum communication. A set of numbers 0, 1, 1, 0, 1, 1, and by measurement. How they will do the measurement, I will show you now. And that uniquely uses this quantum measurement aspect. So you see superposition. How do you create superposition? You spin up, spin down, polarization up, polarization down for light. Only 2 level systems. Ground state 0, excited state 1. So you create these kind of things. Then you apply a matrix called H, Hadamard. It creates superposition 0 plus 1 by root 2, 0 minus 1 by root 2. So these matrices, very simple, 1 by root 2, 1, 1, 1 minus 1. You can actually check that is a unitary matrix. U dagger is equal to U inverse. And rotation is H. So if you are planning to use a quantum computer like IBM, you can actually drag it and put after 0, okay, and you will create a superposition 0 plus 1 by root 2. Now, what is interesting about this 0 plus 1 by root 2? It's a superposition of 0 and 1. 0 and 1 would be like spins up and down. For example, this 0 is along this direction, 1 is along this direction. 2 level systems, up and down. It could be typically Z direction. Imagine that these two are the Z direction. One is this side, one is this side. What about this one? Actually, you can check. This is a state along the X direction. Some of you who know matrices, particularly poly matrices, these are eigenstate of sigma Z. They are eigenstate of sigma X. These 3 Pauli matrices, sigma X, sigma Y, and sigma Z, please make yourself familiar. It's called Pauli get. They are matrices. X get is X matrix 0, 1, 1, 0. Z is 1, 0, 0, minus 1. And Y is 0, minus I, 0. These 3 matrices, if you are familiar, almost you can do everything, and also tensor product. Anything you can do in a quantum computer. You don't need too much of mathematics. Now note one thing about measurement, which Bennett and Brassard used in 1984. You see, you created the state 0. Then you put Hadamard. It's like polarizer and analyzer. Then you are creating 0 plus 1 by root 2. You see, 0 goes to 0 plus 1 by root 2. So this object is like an polarizer. But once you go here, you try to find out, is the state along 0 or is it along 1? Now, as I told you, this fellow is along X direction. It's an eigenstate of sigma X. But if you, from the perspective of Z direction, it's a superposition of 0 and 1, positive sign. So if you measure along Z direction, you will find the state will collapse to 0 or 1. So please keep this in mind. You created a superposition state. this state is pointing along z direction, for example, along this direction. After superposition, it is along x direction, for example, this direction. If you measure along this direction, try to find out where is it. Because you are measuring along z direction, you will find state is along this or along this. This is something uniquely quantum. If there is a classical polarization which is along this direction, which is x, because the angle is 90 degrees, it will have no component along z direction. So, because cosine 90 is 0. But here, as if it's quantum, if it is pointing along x direction, 0 plus 1 by root 2 or 0 minus 1 by root 2, which is along x direction. If you measure and try to find out what is this value along z direction, you will find out it will be 0 or 1. What would you know exactly which one? That nobody knows. It's completely random. So therefore, quantum mechanics is intrinsically statistical. It has certain randomness built into it. So which we have made use of, and we have created quantum random number generator using this fact that measurement can randomly produce 0 or 1. Only if you do large number of measurements, we find out amplitude is 1 by root 2. 1 by root 2 square is half. Half the time you will find 0, half the time you will find 1. So this coefficient number is called the amplitude. The state is 0. Amplitude and state. So it's probability amplitude. More square of that is the probability. So probability half is state 0, probability half is state 1. If you do thousands of measurements, half of the time you find it state 0, other half you find state 1. And you see, if the state is along x direction, you would expect that you will have no component along z direction. Because we have seen, if the vector is along this, cosine 90 is 0, it will have no projection along this. But quantum world is very different. The moment you measure, you try to find out, you find it as a projection. And completely arbitrary. But that arbitrariness helps you. In which way? That if you do thousands of measurements, half the time along this, other half along this. So average will come out to 0. So classical mechanics results emerges in the form of an average. So there are well-defined routes how to go from quantum to classical, called statistical interpretation of quantum mechanics, and this is how it is. For this fact that measurement can lead to collapse, we have been used in BB84 to come up with a secure communication algorithm. Because Alice and Bob, they would know what kind of state they are producing. Any other party called the Eve, the villain, would not know. So Eve tries to measure, since she does not know what state it is created, it will lead to collapse of the state. If there is a collapse of the state, then Alice and Bob would know that somebody is trying to see through their quantum key. So this is precisely BB84, a single state, superposition, measurement leading to collapse, and by mutual talking to each other, they establish a key. All single qubit, very readable. And then quantum key distribution, after that came quantum random number generator. That every output is random, either 0 or 1, nobody knows. Like your coin tossing. 50% this, 50% that. That has led to random number generator. They are available in the market, you can check. The US is broadcasting these kind of random numbers. Now, what are the quantum gates? So, Hadamard is what I have introduced to you, which leads to quantum superposition. Now, I am telling you the one more gate I did for control not. Here, B is controlling A. If B is 0, whatever A has stays like that. You see, A has 0, output remains 0. B is 0, A was 1, nothing happens. But if B is 1, A will change. You see, 0 becomes 1. 1 becomes 0. So this is called control not. Notation for that this fellow is controlling this guy. Control and target. Control not. Okay. So these are the matrices which you need. Nothing more is required for to do universal quantum computation. And as I told you, Toffoli without knowing has invented a unitary matrix called Toffoli gate, which was reversible. Tommaso Toffoli, basically 3-qubit gate. Control not. In our modern language, control not. The truth table is here. So this is reversible. Hence the matrix is unitary. So these are the things what you need. And you can design something called universal quantum computer. Nothing more you need. Okay. What are the types of quantum computer available now? Annealing, quantum annealer is available. Annealing means, you cool down, and in the ground state, you will actually find the answer to your quantum problem. Quantum annealers. These are basically, principles of quantum mechanics which is used for designing a quantum computer. Analog quantum computers, many of the companies are at it. Google, Microsoft, many of them. IBM has been fairly successful in doing so. There are many, many companies who are into this business. I showed you some of their pictures. Okay. Now, this Bell state has played a very key role. So therefore, I would like to emphasize on Bell state. So Bell pointed out that there is a very quantitative way of predicting if quantum mechanics is right or wrong. So Bell state is a 2-qubit state, singlet or a triplet. 1 by root 2, 0, 0, plus 1, 1, like that XX plus YY, or 1 by root 2, 0, 1, plus minus 1, 0. They are examples of Bell state. 2 particles, there will be 4 of them. 4 states are there. So what Bell pointed out, that if you do Bell measurements, remember I showed you that correlated measurements, coincidence measurements, those are called Bell measurements. You have to simultaneously find out the state of both the particles. And Bell pointed out that if you do that kind of measurement, you will find something very interesting, that there is a limit what you observe. I'll show you about that. That when your measurement will give you classical. If it is classical, it will value you lie between 2 and minus 2. If it's quantum, then it will be 2 root 2 and minus 2 root 2. You see this 2 root 2. That played a crucial role. And experimentally, every time they take an entangled state. With Bell state is an entangled state. We always find 2 root 2. For separable, answer no. Separable state is some extent are like classical. See here, for example, then you question arises, how do you clear them? If you see this kind of circuit, you will encounter. In an IBM or any machine, you will encounter 0 and 0, they are separable states. 2 up spins, if you have, they are like separable. Most like classical, nothing more can be done. Then how do you entangle them? You create, first of all, Hadamard, superposition. After Hadamard, it becomes 0 plus 1 by 2. Then apply control knot. So using that, you can actually create all the 4 Bell states. Okay. So I'll show you these 2 and where are the other 2. They are the other 2. You can create all these Bell states using this approach, starting from separable state, Hadamard control knot. And Hadamard control knot are the universal quantum gates. So it was John Bell who came up with a testable prediction of quantum mechanics. You measure these objects, the value will be 2 root 2 minus 2 root 2. And in some way, this Bell measurement actually quantifies quantum mechanics. Then later on, Greenberger, Horn, and Geisinger. Greenberger was my teacher in City College. They did a very simple generalization. Instead of 2 qubit, they start with 3. Created this state. Looks very much like your Bell state, isn't it? 0, 0, 0 plus 1, 1, 1 by root 2. Bell is 0, 0 plus 1, 1. Then you may ask, what is the big deal about only one fellow? Big deal is that this has much stronger correlation. So that's the reason it was named Greenberger, Horn, Geisinger state. All these 3 of them are fortunately alive and doing well. Greenberger was my teacher. Greenberger was my teacher in City College. These are stronger correlation, and they are actually very useful. You will find out many applications have come through GAZ state, many of them. And its correlation property is not still very well understood. So people are still playing around with GAZ state. What kind of things you can do? As I told you, give me an entangled state, like Bennett pointed out in 90s, you can do miracles. You don't have to understand what is what is your EPI paradox, what is non-local correlation, but you can use it. And that's what the engineers did. They took a Bell state, they teleported quantum information from one party to another, far, far away, like in Star Wars movies. Now, for example, with hundreds of kilometers, you can teleport. Quantum information can be safely transmitted. Why do you mean by safely transmitted? You will find out that amazingly, the party who is sending, like Alice, would not even know what she is saying to Bob. For that information will be exactly reproduced at the Bob's end. Bob would not know what information he needs. Alice would not know what she is saying. But it can be, information can be teleported. And it does not go faster than light. So there is a limit to the speed of light. So this is unique, that if it succeeds, because it is a deterministic algorithm or deterministic procedure, information will exactly go from Alice to Bob. Alice would not know what information she is sending, Bob would not know what he has got, but you can theoretically show that it goes even if they don't know what the information is. That is uniquely quantum teleportation. Information sending, nobody would know. Very useful because you are sending it, your president has given you something to send it to somebody else, you don't have to know what it is, so you can carry it without knowing. Now, how do you teleport? Now that I have come up with circuit language, so I'll show you that if you want to teleport this object Q0 to this side, Q0 is an unknown state. These are the kind of gates which you have to employ. So Hadamard I have told you is a matrix. Control not also I have shown you what it is. Hadamard is a 2 by 2 matrix, 1 by 2, 1, 1, 1 minus 1. Control not is a 4 by 4 matrix, which is 1, 1, 0, 1, 1, 0. Rest of the elements are 0. This refers to this arrow with semicircle is measurement. You are doing measurement. Now this refers to control Z operation. What is control Z operation? If this flow is 1, on this side, the matrix Z, which is 1, 0, 0, minus 1, sigma Z will be operated. If this is 1, this side, X will be operated. What is X? 0, 1, 1, 0. You will find out that through that only you can teleport the information from this side to that. So very good. So teleportation I can do. Now, if you want, you can check. You know that many countries have come up with teleportation, China being one of the key leaders in it. Now, for example, suppose there's a quantum computer. But the entangled states are key to quantum computer. If they are there, not there, nothing can be done. No quantum computation can take place. Now, suppose somebody has mischievously touched the quantum computer, or because of decoherence, Bell state is gone. Instead of an entangled Bell state, you have a separable state. Then there cannot be any quantum computation. So can you check it periodically if your state is Bell state or not, or entangled state or not, without destroying it? Because you measure, if it gets destroyed, then your quantum computer is gone. So this is basically, you want to know that if your Bell state is intact or not without destroying it. This was my first venture into quantum world, and with a student called Manu Gupta, who is an engineer, electrical engineer, electronics and communication from the JP Institute of Technology, Noida. I did this piece of work. You see, Hadamard control lot has been used, and measurement takes place here. These 2 bits are called ancilla bit. Real quantum objects are here. This is your entangled state. At the end, entangled state remains intact. But I have got the information. I can find out what state here it is without doing measurement on ancilla, without disturbing it. This is the main purpose, that you are not disturbing the state which you have created, but you know what it is. This was fortunately experimentally verified by Professor Kumar. If some of you are curious, you write to me or you can check it out. Now, they told you, whatever you are doing quantum computation, you have to keep certain things in mind. One of them is no cloning. You cannot create an unknown state. Okay? If the state is unknown, you cannot xerox it. So, it was 1981, quite some time back. So now that plays a very key role. So as I told you before I wind up, some of the nice papers I would like you to read. I have 5 more minutes there. This is Bell's paper, a very readable paper, 64. Lot of work is still going on. EPR paradox, hidden variable, all those things. Now this was my teacher, City College, City University. Okay, GZ State. And Professor Zeidinger is a leading scientist in Austria. Professor Horn is doing quantum information. Okay, now I can show you that Bell's inequality or the so-called non-locality, people are testing all sorts of things. And now people are promoting technology. For example, here there is something called steering. This idea was known to Schrodinger, by the way. Schrodinger knew entanglement. He actually wrote the word entanglement and showed what does it mean. He similarly used the word for steering. This non-locality can be used to do some practical things, just like here. But, we physics people have been bogged with it. But engineers like you, for example, have made use of it very extensively. So I would say that please play around. Here is another one. Entanglement between superconductivity is a very recent paper. This tardigrade is apparently some kind of an insect. Check it out, because this was the first time I heard this name. Superconducting qubit, and this fellow has been entangled. This fellow really means is atom. One atom from there has been entangled. This is a very recent one. So people are beginning to do all sorts of weird things. And people claim that, for example, photosynthesis, there is some quantum coherence, quantum entanglement is there. So the quantum world is opening up. Both technology, secure communication, quantum internet, quantum coins. You can check out. We have some work on quantum checks. Then, for example, non-fungible tokens, quantum Bitcoin. Quantum Bitcoin is also there. Now, 3 questions are asked. Your ma'am told me to answer 3 questions. One was, for example, quantum. In the context of quantum network, is it possible to have quantum blockchain? Answer is yes. In fact, if you are curious, I'll show you that paper. We were one of the first people to do it. It's published in Physical Research. And Shreya Banerjee and myself and one more student. Quantum blockchain. What is blockchain? Is that you can have a group of people, where your information will be spread. And here entanglement plays the key role, where because of which information gets spread between many particles. So in fact, in principle, you can have a quantum blockchain. People have demonstrated it, like us, for example, in a small scenario. You can extend it. Hopefully in future, the quantum network will come. Quantum blockchain also will become reality in a big way. Similarly, for example, what are the other things where you can make use of quantum technology? You name it, you have it. Like medical, brain imaging, many areas, entangled photons are coming into play. For example, you can actually do even, this kind of, something called shadow imaging. You don't go into a system, you send one particle, that particle will get absorbed. On the other side, you'll have imaging. So many things you can do. Sensing, imaging, and, manipulating quantum states, making it work for you. So the whole world is open for you. Thank you for inviting me also.
Thank you, sir.
Thank you, sir.
Definitely, sir. I hope this creates an understanding and exposure to your works and the way, like a communication platform to reach to you. And thank you so much again, sir, for accepting my invite. And thank you very much for joining, sir.
Yeah, thank you. Thank you. Good night.
Hope, yes, sir. Thank you, sir.
Thank you.
Thank you.